All right, so on your handout, we've got the radical symbol. Everybody knows what that looks like? You got whatever is underneath your radical symbol is called your radicand, and then the whole entire expression is called a radical expression. On your handout, it says the definition of a principal square root is always a positive number. So if somebody says, what's the square root of 25? It's just a 5. Later on when we start to solve, we might say that the square root of 25 could be positive 5 or negative 5. But if somebody just says, what's the square root of 25? It's 5. What's the square root of 100? It's 10. What's the square root of 4? It's 2. That's called the principal square root. So looking at example 1, these first few will go pretty quick. What's the square root of 49? 7. Example 2 has a negative out on the left-hand side. It's okay if the negative is outside the square root. We just bring that negative down with our answer. So the negative square root of 49 is going to be negative 7. Example 3, it's not okay for a negative to be underneath the square root. Okay, when you take the square root of negative 49, you can't say it's 7 because 7 times 7 is positive 49, and negative 7 times negative 7 is positive 49. The square root is asking you what times itself 2 times is that number. So there's no answer for this one, and it's because it's really an imaginary number. So right now we're going to say no real number because all the numbers that we've studied so far are real, and the square root of a negative number is actually not a real number but an imaginary number, and we don't know what that is yet. We'll talk about that several weeks from now. Example 4, you're going to take the square root of a fraction by taking the square root of the top. The square root of 4 is 2, and you're going to take the square root of the bottom, which is 3. So the square root of 4 over 9 is 2/3. If you have any operation to do underneath your radical sign, you're going to go ahead and add, subtract, multiply, or divide and get one number. So 3 plus 22 is 25. So that problem really says the square root of 25, and the square root of 25 is 5. So in example 6, we have something to do underneath our radical symbol. We have to square our 4, and 4 squared is 16, and the square root of 16 is 4. Example 7, we have something to do underneath our square root symbol. We have a negative 4 in parentheses. It's being squared. What's a negative 4 in parentheses squared? 16. And what's the square root of 16? 4. Okay? So the first 7 examples all have to deal with some type of number underneath the square root that is a perfect square. Okay? So we were able to find the square root of every one of those, examples 1 through 7, except for 3, and we can't find 3 because we can't find the square root of a negative number because that's not a real number. Now when we get to 8, 300, the square root of 300, 300 is not a perfect square, so we have to simplify it, and it doesn't mean we get the decimal for it. So we're looking for something squared that is 300. So think of all your perfect square numbers. I'm going to write those on the side. 2 squared is 4, 3 squared is 9, 4 squared is 16, 5 squared is 25, 6 squared is 36, 7 squared is 49, 8 squared is 64, 9 squared is 81, 10 squared is 100, 11 squared is 121, and 12 squared is 144. We could go further with that list, but those are the numbers that you learned how to multiply in the 3rd grade. So what is the largest perfect square number that you can divide into 300? Since 300 is not a perfect square, you're going to have to find the largest perfect square that will divide into 300. Will 144 divide into 300? No. 121? No. 100? Yep. So we're going to rewrite 300 into a number that is a perfect square times whatever 100 times what is 300, and that's going to be 100. 100 times what number is 300? So it's going to be 100 times 3. Okay? Why did we choose 100? It's the largest perfect square. So you want to try to find the largest perfect square that will divide into your number. If in the beginning it's not a perfect square, you're going to simplify by finding the largest perfect square that will divide into that. Do y'all remember from Algebra 1 what you do next? You simplify this perfect square. So what's the square root of 100? 10. And where does the 10 go? It goes outside. So it'll come outside to the left, and then you're left with the square root of 3. So the square root of 300, it is a decimal, but its exact answer is 10 square root of 3. So that's what you're going to do when the number under your square root is not a perfect square. Example 9, is 32 a perfect square? No, it's not. Will 144 go into it? No, those are all too big. So go all the way to 16. Okay? 4 will go into 32, but there's even a larger perfect square number that will go into it, which is 16. So you always want to try the largest one. So that's going to be 16 times 2. Square root of 16 is 4. 4 comes out to the left, and 2 stays underneath. If you would have used the 4, you still could have come out with 4 square root of 2, but you would have to simplify twice. All right, let's look at the next example. I've got to flip over just a second. Example 10. What do you do if you have a variable underneath your square root? Well, one thing that you need to know is that there's an understood little number right here on your radical sign called an index, just like an index card. If a radical symbol doesn't have a little number written there, that little number is an understood 2 for square root. When you're taking the square root of a variable, you're going to divide the understood index into the exponent. So 2 goes into 6 3 times. So x to the third is the square root of x to the 6th. Let's think about that. X to the third is the square root of x to the 6th. So that must mean x to the third times itself 2 times is x to the 6th. Would that work out? X to the third times itself 2 times is x to the 6th. Let's just check that. X to the third times itself 2 times is x to the 6th. Yeah, because what are we going to do with those exponents since we're multiplying? We're adding them. Okay, so that problem says, what is the square root of x to the 6th? So the quickest way to do that is if you're taking the square root, you divide 2 into the exponent. All right, example 11. I don't have an index, so it's an understood 2, and this time 2 does not go into 11 evenly. It does go into 11. How many times? 5. So a to the 5th comes out, but since 2 does not go into 11 exactly one amount of times, there's something left over. What's left over after 2 goes into 11 5 times? A 1. And that 1 is going to be the exponent of your a that's going to be left under the radical. And you won't see that little bit, that 1, but I'm just showing it to you so you can see what we're doing. 2 goes into 11 5 times. 1 is left over, and that 1 is the exponent of the a that's left under the radical. Why is there no radical in the answer for example 10? It went into it evenly. If there's not anything left over, there's no radical in your answer. All right, example 12, we're actually multiplying 2 square roots together. We can do that. We just have to put the answer back underneath the square root. So what's 6x times 3x? 18x squared. So we can multiply 2 square roots together. We just have to put our product back underneath the square root. Is 18 a perfect square? No, what's the largest perfect square that will go into 18? 9. So I'm going to break 18 down into 9 times 2. And then I'm just going to write my x squared. Then I'm going to take the square root of everything I can take the square root of. So can I take the square root of 9? Yes, the square root of 9 is 3. Can I take the square root of 2? No, can I take the square root of x squared? Yes, because the understood index of 2 divides into the 2 that's under the radical, and how many times does 2 go into 2? 1. So x to the 1 comes out. Is there anything left over? Anything left over after 2 goes into 2 one time? Nothing left over. 2 goes into 2 evenly, right? So you're not left with an x under the radical. 2 goes into 2 one time. So x to the 1 comes out. There's no x left under the radical because 2 goes into 2 evenly. It's just that 2 that's left under the radical. It's going to be a hard section for some of y'all. Example 13. Now we're dividing. Square root of 48, 48x cubed divided by the square root of 6x. You can divide square roots. So 6 is going to divide into 48 how many times? 8. X cubed divided by x is x squared. And then we just got to put a square root back over that. You can divide a square root by square root, but once you get the quotient, you got to put it back underneath the square root. Is 8 a perfect square? No. What can I factor out of 8 that is a perfect square? 4. So I'm going to rewrite that as the square root of 4 times 2, x squared. And then I'm going to take the square root of everything that's a perfect square. Is 4 a perfect square? Yes. What's the square root of 4? 2. Is 2 a perfect square? No, so I'm going to have to leave it under the square root. How about x squared? Yeah, what's the square root of x squared? Just an x. Anything left over? 2 goes into 2. Anything left over? Y'all don't get that, do you? Yeah, you're just going to have a 2 underneath your radical. Two x squared root of 2. Let me get through these and I'm going to show you a couple things. I can kind of tell by your silence maybe what you're not getting. Example 14 is showing us how we can add square roots. 7 square root of 3 and 5 square root of 3 are considered like terms because they both have square roots of 3's. Anytime you're adding or you're subtracting and you have two radicals that are exactly the same, you leave the square root of 3 and you just combine the numbers out in front. So 7 and 5 combine to be 12. Anytime you're adding or subtracting, you just keep that radical. It's like a like term. It's like you're adding or subtracting x's. Alright, square root of 3 is simplified. There's no number that will go into 3 that's a perfect square, so 12 square root of 3 is the final answer there. In example 5, it looks like we can't add to begin with because one term has a square root of 3 and the other one has a square root of 12, but 12 is not simplified, okay? 2 square root of 3 is simplified, but 5 square root of 12 is not simplified. What perfect square goes into 12? 4. So you're going to break 12 down into 4 times 3. 2 square root of 3 is simplified. 4 is under your square root. Take the square root of 4 and get what? 2. What happens when 2 comes out and there's already a number outside? They get multiplied together. So when the square root of 4 is 2 and 2 comes outside and there's already a number outside, you do 2 times 5 and you get 10 and the 3 is left under the radical. Now you can add 2 square root of 3 and 10 square root of 3 because those are considered like terms. And 2 plus 10 is 12. Keep the square root of 3. Questions about 15?
Can you go over that again?
Which part?
Where you have 2 square root of 3 plus 5 square root of 4 times 3.
Yeah, I don't see how you're getting the 10. Yeah, I don't see where the 2's.
Okay.
The 4 goes away.
I'll show you this step. So y'all will probably, when the square root of 4 is 2, the 2 comes out. If there's a number already on the outside, those numbers get multiplied together. So y'all will start to do that in your head. The square root of 4 is 2. 2 comes out. If there's already a number on the outside, you multiply those numbers together. So that gives you 2 square root of 3 plus 10 square root of 3.
But why did the 2 come out? Like, why?
Square root of 4 is 2. We took the square root of that 4. And then we add the 2 and the 10. All right, 16. Y'all just hang on. Let's get through these notes and we'll work through any problems that y'all have tomorrow. All right, so what's underneath the first radical that's not a perfect square? 50. What can we divide into 50 that is a perfect square? 25. So let's change 50 into 25 times 2, and let's keep the x. 32. I think we've seen a 32 already today. 4 will go into 32, but what number larger than 4 is a perfect square that'll go into 32? 16. So let's change 32 into 16 times 2, bring down the x. See if y'all can do this one now. What's the next step going to be? Okay, so the square root of 25 is 5. It comes out. It gets multiplied times the 4, and then I have a 20 square root of 2x. Then I take the 16, I take the square root of that, which is 4, and I do 4 times 6, which is 24. So I have minus 24 square root of x. The last one should be square root of 2x, my bad. Now you have like terms because both terms have square roots of 2x's, so what's 20 minus 24? Negative 4 square root of 2x. Believe it or not, y'all did all of this in Algebra 1. How many of y'all, it's been since 8th grade since you took Algebra 1? All right, we got about 7 minutes. Hang on. Y'all ready? All right, rationalizing the denominator. Let me page over. No radicals are allowed in the denominator. That's a big time rule. No radicals are allowed in the denominator. If you have a radical in the denominator, you've got to do something to get rid of that radical in the denominator. That something is called rationalizing the denominator. So in example 17, I can't have the square root of 6 in my denominator. So what you're going to do is you're going to multiply the top and the bottom of your original problem by the square root of 6. If you have the square root of 2 in the bottom, you're going to multiply the top and the bottom by the square root of 2. That's going to get rid of the square root in your initial problem. You're going to do top times the top. Since 15 is not under the square root, when you multiply 15 times the square root of 6, you just get 15 square root of 6. You can't multiply 15 times 6 because 15 is not under the square root. But on the bottom, you can multiply the two 6's together because they're both underneath the square root. So that's going to give us the square root of 36. And then that square root of 36 is going to turn into a 6. So by multiplying the square root of 6 times the square root of 6, that's the way we can get rid of the square root in your denominator. The top just stays 15 square root of 6. The only thing that you could reduce are the 15 and the 6. You can't touch what's underneath that radical with any number that's not under a radical. So will 15 over 6 reduce? Yeah, 3 will go into the top and the bottom. And you're going to end up with a what? 5 square root of 6 over 2. Example 18, 12 divided by the square root of 8. We got a square root of 8 in the bottom, and we don't need a square root of 8. You could multiply the top and the bottom by the square root of 8 over the square root of 8. That would work, just like we did in example 17. Or there's a smaller number that you could multiply by. What's a smaller number that you can multiply 8 by that'll give you a perfect square? 8 times 4 is 32. 32 is not a perfect square. What's a smaller number than 8 that you can multiply times 8 that gives you a perfect square? 2. So you could do square root of 2 over the square root of 2. Whatever you multiply by has to be on the same as the top as it is on the bottom. The reason I'm choosing 2 here is because 8 times 2 is 16, and that's a perfect square. And you could use 8, but it's just going to make your numbers larger. So you could multiply by square root of 8 over square root of 8, but 2 is going to make the problem a little bit simpler. What's 12 times the square root of 2? 12 square root of 2. What's the square root of 2 times the square root of 2? Excuse me, what's the square root of 8 times the square root of 2? Square root of 16. See anything that will simplify? Square root of 16 will turn into what? 4. See anything else that will simplify? 12 divided by 4 is 3. 3 on the top or 3 on the bottom? 3 on the top. So your final answer is 3 square root of 2. You cannot have a square root in your denominator. It's just one of those math rules. All right, last example. 7 divided by 5 plus the square root of 3. So in example 19, you have 2 terms in the bottom, and one of those is a square root. Anytime you have 2 terms, and one or both of the terms are square roots, you have to multiply by what we call the conjugate of 5 plus the square root of 3. And that's going to be 5 minus the square root of 3. We're going to rationalize this way anytime there's 2 terms in the denominator. If it would have been 5 minus the square root of 3, then we would be multiplying by 5 plus. So all you're really doing is just changing that sign. Whatever you multiply on the bottom, you also have to multiply on the top. Okay?
You got 2 different numbers in the denominator. You do the opposite of what the...
That's called the conjugate. You're going to do top times the top and bottom times the bottom. So when you do top times the top, it's like you're distributing the 7. 7 times 5 is 35. 7 times negative square root of 3 is negative 7 square root of 3. And then on the bottom, you're going to do 5 times 5, which is 25 square root of 3 times negative square root of 3, which is negative square root of 9. Then the square root of 9 is going to turn into a what? Just a 3, right? And you're going to have 35 minus 7 square root of 3 over what number? 25 minus 3, which is 22. All right, that's going to be your final answer unless 35, 7, and 22 all have a number that will divide into all 3 of those. You can't touch the number under the square root. But I don't think there's a number that will go into 35, 7, and 22. Okay? You took these notes so you could use them for your homework. Do the best you can with your homework. And again, every day when you come in, we'll go over that homework. We'll work on anything that you don't know how to do.